Bismillahirrahmanirrahim. Assalamu alaikum dear viewers, I am Dr. Noshin Afshan. I hope that all of you would be fine and I am thankful to you for watching this video. So our today's lecture is about hybridization, in which we will discuss the introduction of hybridization and then its categories, and later on we will apply the rules of the hybridization with respect to different examples of the organic compounds. For example, alkanes, alkenes, alkynes, alkyl amines, alkyl imines, carbonyl compounds that are aldehydes and ketones, and nitriles. So now let's begin. So first of all, we will start from the introduction of hybridization. That is the intermixing of atomic orbitals of the comparable energies to form hybrid orbitals of the equal energy and same shape. And before their intermixing, their shapes are almost identical or comparable. Comparable means the s orbital would intermix with the s orbital as well as px orbital. And also s orbital would intermix with 2py and 2pz orbitals. Similarly, there are some conditions that how orbitals can intermix to form the new hybrid orbitals. So in this way, we may say that the intermixing of atomic orbitals of comparable energies and almost same shapes to form the hybrid orbitals that would have the equal energy and the same shape. For example, we will see in the sp3, sp2 and sp hybridization. And in these cases, there are different orbitals that take part in the process of intermixing or in the process of hybridization, that are s orbital, p orbital and d orbital as well in the higher categories of the hybridization. So now there are main categories of hybridization are sp3 hybridization, where the alkanes follow up this type of category of hybridization. And our next category is sp2 hybridization, where alkenes and alkyl amines would follow this category of hybridization, that is sp2. And our third category or the third main category is sp hybridization, that is followed by alkynes and nitriles. So let's discuss their details. So first of all, there is the sp3 hybridization. In this type of hybridization or in this category, one s orbital would intermix with three p orbitals, that are px, py and pz. And all of these atomic orbitals would belong to the same shell of the atom. So they would intermix to form four new equivalent orbitals, or that are also called as hybrid orbitals. And these hybrid orbitals are called as sp3 hybrid orbitals because here one s orbital has been taking part and three p orbitals are taking part. So the overall number of hybrid orbitals would become 4. And the number of p orbitals would be highlighted in the form of superscript of the p, that is sp3. Now the next point comes for their orientation in space. These hybrid orbitals would be directed towards four corners of a regular tetrahedron, where the angle between every two sp3 hybrid orbitals would be 109.28 degree. And in this case, every sp3 hybrid orbital would have 25% s character because there is one s orbital and 3 p orbitals, and so there would be 75% p character. For example, methane, ethane and methylamine. In the case of methylamine, both carbon and nitrogen molecules would follow sp3 hybridization. So, these examples have been explained here. First of all, we discuss the structure of methane. We will start from the electronic configuration of carbon atom, as the atomic number of carbon is 6. So at ground state, its configuration would be like 1s2, 2s2, 2px1, 2py1 and 2pz would be empty. But at the excited state, the one electron from the outer shell would be transferred to the here the one electron in the outermost shell, that is second shell, and here that resides in 2s orbital. So this would jump from 2s orbital to 2pz orbital, and in this way these 2s, 2px, 2py and 2pz orbitals would be partially filled. And these atomic orbitals belonging to second shell of the atom, that is the valence electrons residing in these orbitals, would intermix or hybridize together to form 4 sp3 hybrid orbitals. So this point is to be noted that the inner shell orbitals, that is one s orbital, would never take part in this type of hybridization because here there are only two shells, so the atomic orbitals in the valence shell would only take part in the process of hybridization and not the inner one, that is 1s. And here these 2s and 2p3 orbitals are going to hybridize together to form sp3 hybrid orbitals, which will form 4 sigma bonds. And how they will be oriented in space here? This shows the tetrahedral geometry here, that is directed along the one corner of the tetrahedron, and here these are directed towards the other three corners of the tetrahedron. And every sp3 hybrid orbital over here has been forming a sigma bond with the 1s orbital of the hydrogen, and the simplified line structure would be drawn here, that is showing that 109.28 degrees bond angle between every HCH. So the details of this structure are like this. So here the atomic orbitals have been drawn with respect to their energy levels. The 2s orbital having electron pair would reside at the lower energy state as compared to the 2p orbitals. And when these atomic orbitals s and p orbitals would intermix to form hybrid orbitals, then the energy level of the hybrid orbitals would lie in between the energy levels of 2s and 2p orbitals. So here all 4 hybrid orbitals would have the equal energy level, having 1 electron in each and of the same shape as have been drawn here. And these four sp3 hybrid orbitals of the carbon atom would be oriented along the four corners of a regular tetrahedron, and every sp3 hybrid orbital would share its electron density with the one electron that resides in the 1s orbital of the hydrogen. So here the overlapped region has been shown with an electron pair. So the next one is structure of ethane according to hybridization. Here the electronic configuration, as all of you know, that at the ground state and at the excited state it becomes 1s2, 2s1, 2px1, 2py1 and 2pz1. And here we are talking about the hybrid orbitals of one carbon atom in the case of ethane molecule, because both of the carbons would behave identically. So at one carbon atom the situation would be identical with that of the other carbon atom. So we may consider any carbon atom here. That is why, for the sake of simplicity, we consider the atomic orbitals of one carbon atom, that are 2s and 3 2p orbitals. So these would hybridize together to form 4 sp3 hybrid orbitals, same like methane molecule, but the only difference here is the 3 sp3 hybrid orbitals would overlap with 1s orbitals of the hydrogen atoms, and in this way here the 3 sigma bonds would be formed with hydrogen atoms, but still these three would be oriented at the three corners of a regular tetrahedron, and the fourth sp3 hybrid orbital of one carbon atom would overlap with the sp3 hybrid orbital of the other carbon atom, and that would be pointed out towards the fourth corner of the tetrahedron. And in this way, these sp3 orbitals overlap would result in the formation of a fourth sigma bond. So the overall number of sigma bonds in the ethane molecule would be 7, because 3 sigma bonds with the 3 hydrogen atoms for one carbon and 3 sigma bonds with the 3 hydrogen atoms at the other carbon atom. So the total number of sigma bonds would be 6 over here. The 7th sigma bond would be formed between carbon-carbon, and that would be the result of the overlapping of sp3 hybrid orbitals of the both carbon atoms, as have been shown here. And the simplified line set structure would indicate that still the HCC bond angle would be 109.28 degrees, and also any HCH bond angle would also be 109.28 degrees. So the next category is sp2 hybridization. In this category of hybridization, as its name indicates, that there would be one s orbital and two p orbitals. So the one s orbital and two orbitals of the p orbital belonging to the same shell of an atom would intermix to form three sp2 hybrid orbitals. So in this case, as there are only one s orbital and two p orbitals, so 1 plus 2 would be equal to 3. So these make up the 3 sp2 hybrid orbitals, and as there are two orbitals of the p nature, so that 2 has been indicated as the superscript of this p letter. So the writing pattern would be, there would be 3 sp2 hybrid orbitals, and these would be directed towards three corners of a triangular shape, or making the trigonal planar geometry. And hence the bond angle between every two sp2 hybrid orbitals would be 120 degrees, that is 120 degrees. And here every sp2 hybrid orbital would have 33.3% s character and 66.6% p character. And the examples that follow up the sp2 hybridization are ethene molecule, ethene compound, that is methanol, that HCHCO, and methyl amine. These carbonyl compounds would follow up sp2 hybridization. So now we discuss the structure of these compounds according to sp2 hybridization. In the case of this ethene molecule, every carbon atom has the electronic configuration same like before. At the ground state, the 2pz orbital would be empty, and at the excited state, the 2s and 2px, 2py and 2pz orbitals would be partially filled. So here, the atomic orbitals that are 2s, 2px and 2py, only these three orbitals would hybridize together to form three sp2 hybrid orbitals. And the remaining one, that is 2pz orbital, would remain unhybridized. So this unhybrid orbital, that is 2pz of this carbon atom, would be drawn like this, vertically over these three sp2 hybrid orbitals, and in the same way, at this carbon atom, this unhybridized 2pz orbital would also be drawn like this. So here first of all, we discussed the formation of the sigma bonds, that is these three hybrid orbitals that are sp2 hybrid orbital of this carbon atom would be directed towards the corners of a trigonal planar geometry like this, where they would make up the angle of 120 degree. And here these two sp2 hybrid orbitals would overlap with the 1s orbital of the hydrogen atom, forming sigma bond as a result of the overlapping of sp2 orbital with s orbital. And similarly here, this bond would also be a sigma in nature and has been formed as a result of overlapping of sp2 hybrid orbital with s orbital. And same case would be followed up with this carbon atom. The two sp2 hybrid orbitals would overlap with the 1s orbital of the hydrogen, forming two sigma bonds. And the third sp2 hybrid orbital of both of these carbons would overlap together and would make up a sigma bond as a result of sp2 overlap with sp2 orbital. And here in this way, the total number of sigma bonds in the compound of ethene are 5. One sigma bond is common between these two carbon atoms and 2 on each carbon atom. So the total number of sigma bonds would be 5. And the remaining 2pz unhybridized orbital would overlap side phase, and this would generate a pi electron cloud, making up a pi bond. that would be indicated putting or drawing another line over the sigma bond in the simple line structure of the ethane compound. Here the bond angle between HCC or HCH would be 120 degree. Our next structure is methylamine. Here we have the simple line structure of methylamine is represented here, that is CH3 and NH2. Here we will discuss the hybridization at the carbon atom as well as at the nitrogen atom. And at the carbon atom, as it is forming 3 sigma bonds with the hydrogens and 1 sigma bond with the nitrogen, because here there is not a double or triple bond between any two atoms. So as this is the saturated structure, so all the bonds would be sigma in nature. And here this CH3 group would follow up the same hybridization as in the case of sp3 hybridization in the case of methane molecule. So along this carbon atom, the 3 sp3 hybrid orbitals would form the 3 sigma bonds with the 3 hydrogens, and 1 sigma bond would be generated with the sp3 orbital of the nitrogen over here. Nitrogen would also have the sp3 hybridization and would retain the geometry in the form of tetrahedron. And here along the carbon, this would also has the tetrahedral geometry, where the 3 corners of the tetrahedron would be occupied by these hydrogen atoms, or the overlapping between sp3 and 1s orbital of the hydrogens, and the 4th corner of the tetrahedron would be accompanied by the 4th sp3 hybrid orbital that would overlap with the sp3 hybrid orbital of the nitrogen. So in this case, in the case of nitrogen, the 1 sp3 hybrid orbital would have the electron lone pair or would be completely filled. The 1 sp3 hybrid orbital would be overlapped with the sp3 hybrid orbital of the carbon atom, and the other 2 sp3 hybrid orbitals would overlap with the 1s orbitals of the 2 hydrogen atoms. So in this way, along both of these carbon and nitrogen atoms, the geometry would be tetrahedron and the bond angle would be 109 degree. So this is the compound having a structure representation according to sp3 hybridization. Comparable to it, now we discuss the hybridization structure of methylamine that would have the sp2 hybridization along both of these carbon and nitrogen atoms.
So here, in the case of alkyl amine, where this carbon that is doubly bonded with the nitrogen represents amine group, and in these cases, both of these carbon and nitrogen atoms undergo the sp2 hybridization, and 3 sp2 hybrid orbitals of both of these atoms are oriented in trigonal planar geometry. In the case of this carbon atom, the 2 sp2 hybrid orbitals would overlap with 2 1s orbitals of the hydrogen atoms in the case of methylamine, but in the case of alkyl amines, those sp2 hybrid orbitals of the carbon would be overlapped with the hybrid orbitals of the alkyl group. And the third one, sp2 hybrid orbital of this carbon would overlap with the sp2 hybrid orbital of this nitrogen atom, forming a sigma bond. So in this way, these three sp2 hybrid orbitals would overlap to form three sigma bonds. And the other, or the second sp2 hybrid orbital of the nitrogen would overlap with the 1s orbital of the hydrogen in the case of methyl but in the case of alkyl imine, that sp2 hybrid orbital of the nitrogen would overlap with the other hybrid orbitals of the alkyl group. And the third sp2 hybrid orbital of the nitrogen would occupy a lone pair of electrons. And the geometry of the three sp2 hybrid orbitals in the case of this nitrogen would still be in trigonal planar geometry. And the remaining 2pz unhybrid orbital of both of these atoms, this carbon and nitrogen. So those 2pz orbitals would overlap sideways to form a pi bond that has been represented here in the form of another line drawn over the sigma bond. So in this way, there are overall 4 sigma bonds in this molecule or in this compound and 1 pi bond. So this is the structure of alkyl imines generally and the methyl imine in specific. Okay, so our next category of hybridization is sp hybridization. The specialty of this category is here only one s orbital and only one p orbital belonging to the same shell of an atom would intermix to form 2 sp hybrid orbitals that would be directed in a linear geometry, making 180 degrees as bond angle. And every sp hybrid orbital would have the 50% s character and 50% p character because there are only 2 orbitals over here, that is 1s and 1p. So both of these orbitals would participate equally in the 50% each. And the different compounds that undergo the sp hybridization are ethyne and methyl nitrile or methyl cyanide. So the structure of ethyne compound has been discussed over here. As according to the electronic configuration of carbon at its excited state, this would follow up the 1s2, 2s1, 2px1, 2py1 and 2pz1. So in this way, these 2s and 2p orbitals are partially filled. Since here in the case of ethyne, that is the structural formula of ethyne is CH, that is that carbon is triply bonded with the other carbon atom in the form of CH. In short, that is C2H2. So here the 2s and 2px orbitals would hybridize together to form 2 sp hybrid orbitals, and the remaining one, that are 2py and 2pz orbitals, would remain unhybridized. So in the case of these 2 sp hybrid orbitals, so every carbon atom in the case of ethyne compound would have 2 sp hybrid orbitals, and one of these sp hybrid orbitals would overlap with the 1s orbital of the hydrogen, that is here, forming a sigma bond, and same situation occurs over here with this carbon atom. And the other sp hybrid orbital of one carbon atom would overlap with the sp hybrid orbital of the other carbon atom, forming a sigma bond. So in this way, there would be a total number of 3 sigma bonds in the case of ethyne. And as we already have said that the 2py and 2pz orbitals would remain unhybridized. So here, these red ones show the 2py orbital in both of these carbons, and the blue ones show the 2pz orbitals. So this 2py unhybrid orbital of the one carbon atom would overlap with the unhybrid 2py orbital, forming a pi bond. That has been shown over here in the form of a pi electron cloud, either above or below the sigma bond. And similarly, the 2pz orbital of one carbon atom, that is here, would overlap with the 2pz orbital of the other carbon atom, that is here in the blue shade, forming the pi electron cloud either above or below the sigma bond. Here it is also been shown in the blue color. And this would form a second pi bond. So in this way, there would be a total number of 3 sigma bonds over here and 2 pi bonds. So today's lecture has been completed. So thank you very much for watching the video, and please let me know in the comment section that how much do you like this video. Thank you very much. Allah Hafiz.